analyzing data when you have two groups or two samples. Okay? Now, when I wanted to find out how likely a mean was from one sample, how did I find that out? What probability distribution did I use to find the likelihood of a particular mean? What probability distribution did I use to find the likelihood of a particular mean? This goes back to, chapter 6 and 5. Not exactly. You're sort of going in the right way. But it was called a particular name. I have a mean of a group. How do I find the likelihood of a mean? Even if I'm not doing a hypothesis test, what do I refer to? What kind of probability distribution do I look at? Yes, sampling distribution of the means, right? Take a sample, get a mean, write it down, throw it back. Take a sample, get a mean, write it down, throw it back. And I get a distribution of means. That was my sampling distribution of the means. Okay? Now, with two groups, what do I do with two groups? I still need this probability distribution. Now what I'm trying to find out is not how likely a particular mean is, but how likely is the difference between two means. Right? So like if I have two stats classes and one gets an 85 on an exam and the other gets an 80, right? Their means are 80 and 85. What I'd like to find out is what is the probability of that 5-point difference? So how do I calculate that, or how do I find the probability with that? Well, now I need the sampling distribution of the difference between the means. The sampling distribution of the difference between the means. Now, how would I get something like that? Well, that, in theory, would be something like you have a population. You take a sample. You get a mean. You write it down. Throw it back. Take another sample. Get a mean. Write it down. Throw it back. Now I have two means here. Find the difference between the two of them, and that's 1 point. And I do it again. Take a sample. Get a mean. Write it down. Throw it back. Take a sample. Get a mean. Write it down. Throw it back. And now I have another set of two means, and I get that difference, and I write that down. That's my second point. And I do that an infinite number of times. And that helps me create the sampling distribution of the difference between the means. That's going to be my probability distribution, in essence, my null hypothesis distribution, to find out how likely is any given difference between two means. Okay? So we're going to have to talk about that. Now, if you remember, the mean of a sampling distribution of means was what? The mean of a sampling distribution of means was equal to what? Anybody remember? Yeah. No, it's the population mean, right? Right? The mean of the sampling distribution was equal to the population mean. In this case, the mean of the sampling distribution of the means is going to be equal to 0. Right? Because the center of that distribution is no difference between these two groups. Okay? What was the standard deviation of a sampling distribution? What was it called? The standard deviation of a sampling distribution. Yeah, the standard error. The standard error. Well, now I'm going to need the same thing for this sampling distribution, but it's going to be called the standard error of the difference between the means. Because again, right, I have these two groups, and I have to consolidate it into some kind of number. So that's why when I had one group, I had a mean. Now that I have two groups, I have the difference between the means. I keep trying to consolidate into a number that's representative of the data. So I have this standard error of the difference between the two means. And just to, we talked about this. What does a standard deviation tell me? I keep bringing this up because this will help you figure out all of these things. What does a standard deviation tell me? A regular, good old standard deviation. What is that an indication of? Yeah. Yeah, about on average, how far scores differ from the mean, right? What does a standard error tell me? What does a standard error tell me? How far what is from what? A standard error of the mean is how far Yeah. Yeah. That's how far the sample mean is from the group mean, right? That's my standard error of the means. Now, the standard error of the difference between the means is going to tell me how far this difference is. The difference between group 1 and group 2 is, on average, from this. Okay? So let's say I have two classes and the average difference between them is 5 points. I'm seeing how close that is to the true population difference between all stats class, two sets of stats classes or my stats classes or whatever, however you want to phrase it. Okay? So this is giving me, so the standard error of the difference between the means is giving me an approximate amount of how far this sample difference is from the actual population difference. Okay? Everybody still sort of with me? All right. The standard error of the difference between the means, he has it here. This formula he has written down, you're actually not going to really use it because you'll notice it has sigma, which is the population difference, right? And this subscript, x bar 1 minus x bar 2, is just an indication that it refers back to differences between means. The standard error of the differences between means. Now, why are you not going to use this formula so much? Because again, what are we assuming in here? Here's the variance for group 1, and here's the variance for group 2. What is the assumption? That we have population variances. Once you get to two groups, you almost never have population variances. Okay? So we're going to, I'm going to show you how to replace that to make it easier. But this is a basic idea. Okay? Now, if you have a very large sample size, right? Often you don't have these population variances. You have sample variances. If your samples are large enough, you can just replace that, the sample standard variances for the population variances and get the standard error using this, and then you could calculate a z. This is called a large sample z-test. Okay? Even if you don't have the population variances, if you have large enough samples. How large? 100 in each group. Okay? They have to be really large, 100 in each group, for you to use this test. Okay? This is not the one we're going to use. Because frankly, if you had over 100 in each group, I wouldn't want you to do it by hand. And SPSS doesn't do Z at all anyway. It just goes right into T. Okay? Now, one of the things about this chapter is that there's a lot of formulas. So what I've done is, I'm going to go through them. I'm going to show you various things. But what I've done is I've made up a flow chart. Hang on just a minute, Mark. I've made a flow chart that will help you narrow down which formula you use under which circumstance. So I'll show you that as we go along. It's posted. I'm going to show it to you here. It is posted on Blackboard. Okay, yeah. Move the what? Oh, the podium again. Yes, we will move the podium. Good? Okay. Now, so we're not going to use a z-test. We're going to use a t-test. And the thing about the t-test, there are essentially two main variations of t-test for these two groups. Okay, let me just give you the overview because I don't want you to get confused by it. Two main branches of this t-test for two groups. One is called a separate variances test, and the other is called a pooled variances test. I'm going to be spending more time on the pooled variances test, but I am going to talk about the separate variances test a bit. And again, so he gives you these formulas, so I want to make sure that you understand what's going on here. The numerator is going to stay the same. It's saying how far is this difference from this difference. What's going to change is our denominator, our standard error. Okay? This notation is your standard error of the difference between the means using the sample variances. Right? Because it says S, it doesn't have sigma. That's kind of your basic average t-test formula. Okay? In this separate variances test, this standard error, he's just rewritten this. He's expanded it to do this. So what it's saying is take each variance and divide by what? look at the notation here. You see little n1 and little n2? That means the number in each group, in each sample. If you have a little n with a number underneath, it's talking about the size of the sample for each particular sample. If there's no index, right, if there's no number underneath, it's just an n, that means the number in each group. And I'll try to remind you as we're going along which thing applies to which. Okay? So this is a separate variances t-test. Now the problem with a separate variances t-test is that it doesn't follow a t-distribution the way we think it's going to. And using it is a little controversial, which is why we're not going to spend a lot of time concentrating on it. But I want you to understand it's there, and I want you to understand, because there's going to be a particular issue as to why we would use it. Okay? So that's a separate variances test. What is the one we're going to be using more of? Something called a pooled variances test. Now, that separate variances test I showed you before had its variance over its sample size, right? And its variance over its sample size. A pooled variances test says, no, let's combine the variances of both groups together to get one estimate of the variance, okay? In order to do that, we create something, this s squared p, and that's really what it is. It's hard when you do it in a document, document file as opposed to like an equation thing. So, but it's the s is the squared part, okay? So that's a pooled variance. Look at what it is. Look at that formula. All that is a weighted average of your variances. That's all it's doing. It looks like some kind of complicated thing, but all it is a weighted average of your variances. Right? Now, why would I weight the averages of my variance? Why would I weight them? Why do I weight a mean? Under what circumstances would I normally weight something? You remember? Yeah. Yeah. Yeah, unequal sample sizes. Unequal sample sizes, I usually weight things differently because you want to give more weight to the group that has the larger number. Okay? So a pooled variance is just a weighted average of your variances. And what am I weighting it by? My degrees of freedom. My degrees of freedom. Okay? This is just another formula for the pooled variance. It's just using sums of squares rather than the variances. Why? Because sometimes you might be given sums of squares as opposed to variances. Okay? Now, when do we use this test? And again, this is going to be the one you use more often. You use it when you can make a particular assumption. The assumption is something called homogeneity of variance. Okay? Homogeneity of variance. The assumption of homogeneity of variance is the assumption that the population variances that you're talking about, are equal. Now, two things. The population variances, how do I know if my population variances are equal? Why am I making this assumption? I'm going to look at my sample variances. I look at my sample variances to make assumptions about my population variances. Because that's all the information I have, usually. Okay? That's one thing. The other thing is, what do I mean by equal? Equal variances? Not exactly the same, but close enough. Now, the rule that we're going to use for this class, that you're going to use on exams and things like that, mostly, is that if one variance is no more than twice as large as the other variance, if one variance is no more than twice as large as the other variance, then we say we have homogeneity of variance. Okay? Everybody got that? Right? Yeah. Yeah. That's exactly what you're talking about, right? Yeah, like if I have two groups, right? If I have two groups, one's taking a drug and one's taking a placebo, and I look at the variances for those two groups, what I'm talking about, the assumption I'm making, is that the population variances for everybody who took a drug or everybody who took a placebo, that those variances would be the same. Okay? Good? Okay. Now, the next page, again, more formulas. That's why I've narrowed it down, so don't fret. Okay? So these are the pooled variance. These are pooled variances formulas. The denominator, notice, the numerator is the same in all of them. What's different? The denominator. Why are those denominators different? It's not a big deal. It's just based on what information you have. Like up here, this is the pooled variance. Here, it's just expanded out. Instead of writing S squared P, that's the pooled variance, that's the pooled variance, right? It's just expanded in the formula. Okay? The denominators for these t-tests, all these denominators are the standard error of the difference between the means. They're all this. All of those denominators are standard errors. This is important to know because we're going to be learning t-tests, but then the other thing we'll learn is confidence intervals. And if you remember in confidence intervals, what did I also use? A standard error. A standard error. So we're going to be taking the standard error and using it in the confidence interval as well. So remember, it's the denominator of this t-test. Okay? So one thing I want to mention to you is, look at this top formula for a minute, just because it's easy. You'll notice we're saying how far is this difference from this difference. Usually, our null hypothesis for two groups looks like this. Usually, that's my null hypothesis. Either that group 1 is equal to group 2, right? That there's no difference. Again, a null hypothesis of no difference between these two groups. But another way to write it is that the difference between them is 0. Okay? It's the same hypothesis, just written in different ways. Yeah? Sure. Oh, that's interesting. I wonder, how far up does that go? Wow. Sometimes it's really far down, and sometimes I can go all the way back. So we're hypothesizing a difference of 0 with the null hypothesis. That means that this term is going to fall out, because it's generally going to be 0. So I am not even going to write that usually when I rewrite the formulas, because that section is generally hypothesized to be 0, and we get rid of it. Sometimes we hypothesize a particular difference. Like if I'm hypothesizing a difference in weight between men and women, I might hypothesize a 30-pound difference. If I'm hypothesizing mu1 minus mu2 equals 30, then I would put that 30 in here. But usually it's 0. Usually it's 0. Okay? Now, here's yet one more formula. We're going to do an example real shortly. This is the formula when your sample sizes are equal. When your sample sizes are equal, then the pooled variance is just the average of those two variances. That's easy enough. But then the standard error is just simplified even more. Okay? So, and that's the same as separate variances for two groups. The big difference between separate variances and pooled variances tests are, well, you do them, the difference in when you do them is generally if you have homogeneity of variance or not. If you have homogeneity of variance, you're always going to use a pooled variances test. And if you don't, you would use a separate variances test. Okay? The big difference doesn't really come down to computation of the t-test. Really, the question is which critical value you use. And that becomes that is really determined by degrees of freedom. Degrees of freedom. So, but I'm going to make this simpler for you than it would be if you were like doing it in a graduate class. Okay? But basically, that's what it's going to come down to. And what are my critical values? Those are cutoffs for rejection. So they differ slightly depending on whether you're using a separate variances test or a pooled variances test. Okay, now let's do an example. A cooperative learning example. Here's our example. An educational researcher is interested in whether children learn better by themselves or in cooperative learning pairs. She randomly assigns 16 middle school children to one of two groups. In group 1, the children learn individually, and in group 2, the children learn in mixed gender pairs. The children are given a novel topic to study and then tested on the topic. Okay, first question. Is this a true experiment or a quasi-experiment? Is it a true experiment or a quasi-experiment? Remember the difference between true and quasi? Are these groups pre-existing, or has the researcher? Yeah. No, but thanks for answering. No one else was willing to. Yeah. You don't ever remember learning that? Does anybody else ever remember learning this possibly? Okay, I see some of you shaking your heads. The rest of you are like, is this statistics? Yeah, somebody else. Did you? Yeah. Yeah. The difference between a true and a quasi-experiment is that if it's a pre-existing group, you can't randomly assign people to the groups. That's a quasi-experiment. A true, it's a pre-existing group, right? A true experiment is when you can randomly assign people to the groups. And that doesn't change your computation, but it changes how you can interpret your data. You can't even talk about causality if you have a quasi-experiment. You can talk about relationships, but...
So I think we learned about this just using experimental.
Okay, I mean, I know it's in the book, so, you know. But yeah, but it's, essentially the same thing. Yeah. Okay? So yeah, so this would be a true experiment because you can randomly assign them to groups. All right, so look at what we have here. First of all, look at the means. Okay? And I guess this must have been scores out of 10 points or something like that. And we see that the kids in the alone group didn't do as well as the kids in the cooperative learning group. Right? The question is whether that difference is just chance or whether it's so rare that we think it was really due to being in a cooperative learning pair. That's really what the question is. Okay? So how do we do this? Okay, the first thing we're going to do is, and you notice, what do I give you? I give you sums of squares, and I give you your sample sizes. Now I'm going to show you the flow chart, which is great when I have overhead projectors. Not quite as great with document cameras. Okay, we will try to make do with that. All right, so essentially, what I've done is given you 3 questions to look at. Okay? The first question is, are both sample sizes large? Again, what do we mean by large here? 100 in each group. 100 in each group. Okay? So if it's yes, then you can use the z-test, the large sample z-test, Just replace all your sample statistics for those population parameters, you're fine. Okay? Likely to happen? Not so likely. Okay? If no, then go to question 2. Question 2 is, are the sample sizes equal? Because if your sample sizes are equal, you also have fewer problems. Okay? So if the sample sizes are equal, then you could use the pooled test, the pooled variances test for equal sample sizes. Okay? And that's right over there. If no, if they're unequal sample sizes, that question says check for homogeneity of variance and go to question 3. So how are we going to check for homogeneity of variance? Well, it says at the bottom, I have like 3 various ways, but the first one is the most important way. Okay? Check the sample variances. I know you can't read this, but what was the rule I gave you before? If one variance is no more than twice as big as the other one, you assume homogeneity of variance. You're going to be using this for your exams. So I'll talk to you about the other tests for homogeneity of variance, but this is the one you're going to be essentially using on exams. Okay? So if your variances are equal, so you use a regular good old pooled variances test. I put that one there. There's a couple other variations. I don't care which one you use. If no, then you'd have to use a separate variances test. And the separate variances test would be this one. We'll talk about that when we get to an example of that. Okay? So for this example, go to the first question. Do we have large sample sizes? No. Do we have equal sample sizes? Yes. Okay, so we're going to use the pooled variances test for equal sample sizes. So that's what we're going to do with this example. Okay, so again, these are our null hypothesis. This is our null hypothesis. Or okay, a hypothesis of no difference. Our alternative is that they're not equal to each other, or that the difference is not equal to 0. Now, it's the pooled test for equal variances. What am I missing in the data I gave you? What did I give you data-wise? What are you missing? The variances, right? Because I gave you sum of squares. If I give you sum of squares, how do you get a variance? Divide by degrees of freedom. Degrees of freedom. We're talking about samples. Degrees of freedom. Right? You're doing it for each one. You're doing it for each one because you're just getting the variance for each group separately before you start putting it into your T formula. What are the degrees of freedom for this group? Yeah, 7. And then for group 2, it's also 7. Okay, so now I have my variances, so I can do my t-test. All right? Okay, so here's the t-test formula for equal variances. I'm going to leave out that other part of the numerator because we're hypothesizing a 0 difference. Okay, big question. What is n? No. Remember, it's a small n here. 8, right? Small n is the number in each group. If there's no subscript, right, that says it belongs to this group or the other group, it's the number in each group. And these groups have the same sample size. So the small n here is 8. Like I said, this is going to be the question all semester is what is n? Okay. That's 0.483. Yeah. Because there's no subscript to it. Little n means the number in each group. The number in each group. Okay. So again, what did I do here? All I did was I took a difference of essentially 3.5 points between these groups, and I turned it into a t. That's what I did, right? I turned it into a t because I can look up the probabilities for it. Okay? So what do I do now? I've transformed this into a t. What would I do now, normally, based on everything you've learned? Yeah? Yeah, I'd have to compare it to a critical value. I'd have to compare it to a t critical value. Okay? So let's actually do that because there's a couple other things I want to say about this, but let's get it. I have to get a t critical value, so what do I need to find a critical value? Degrees of freedom. Degrees of freedom for two groups. Now, I'm going to give you the formula. One easy way to think about it is you're taking off a degree of freedom for each group. So when you had one group, what were degrees of freedom? N minus 1. If you have two groups, it's n1 minus 1 plus n2 minus 1. The easier way to write it is this. But like I said, I just kind of like thinking about it as taking off 1 degree of freedom for each group. Okay? So what are the degrees of freedom here? 14, right? So we have 14 degrees of freedom. We'll assume alpha to be 0.05, two-tailed. So now 0.05, two-tailed, 14 degrees of freedom. So my t critical values are plus and minus 2.145. Yeah. Well, first of all, the question basically asked, are these kids different? Right? It didn't say, does cooperative learning make them better or make them worse? Right? It wasn't giving us a direction. Just does it change it? Okay? So now, what do? Right? Now we have to make a decision. Well, let's just draw this. You could figure it out, but let's just draw this for a minute. So my 2.145 right? Those are my critical value cutoffs. Okay. Do I reject or do I fail to reject? I reject, which means what? Are the kids different or not? Yeah, they're different. They're significantly different. Where is the t observed that I got? It was minus 7, right? Minus 7.985. It's almost minus 8. Where is it? It's like off the page. It's like here. Okay? So one question is, what's the probability of that 3.5 difference given my samples of 8 students in each? What's the likelihood of that happening? You can't give me an exact number, but you can give me a relative number. The probability of that 3.5 difference is what? The probability of it happening is big? No, it's small. How small? Yeah? Exactly, right? Less than 0.05 two-tailed. Way less. If you see a t of 7, you don't even usually have to bother to look it up. Okay? But it's less than 0.05 two-tailed. at least based on what we've looked up. Okay? Now, does that negative, it was negative 7.985, what does that negative tell us? Why is it negative? You could even do this as absolute value if you are paying attention to what you're doing. But why is it negative? That's 7.985. Why is it negative? Yeah. Well, because the smaller mean went first, right? So it's arbitrary, right? If I decided to call the cooperative learning kids group 1 and the alone learning kids group 2, then it would have been a positive 7. So that negative sign is essentially arbitrary. Really, you're looking at the difference. You're just looking at the difference. Okay? Questions? Questions on any of this? Where did it come from? What does it mean? What's the interpretation? Because you see, as I told you, right, it just changes. The details change for these hypothesis tests as you get to 2 groups or 3 groups or whatever. But the basic form, the basic setup is the same. Okay, good. So what are the limitations of statistical conclusions for this? Okay, first of all, a significant result tells us nothing about the magnitude or importance of a difference. It tells us that these 2 groups are different not by chance, but it doesn't tell us if we care, if this is an important difference. So that's going to be in Chapter 8, and that's an important thing to include. Right now, all we're seeing is this is different, this is not different. As a matter of fact, what's going to give us more information than just a hypothesis test? What's the next thing that's going to give us more information about this than just a hypothesis test alone would give us? Confidence intervals. Confidence intervals. Okay? So that's what we're going to do. We're going to do a confidence interval. And then that last point is, again, is what I mentioned about quasi-experiments. So the next example, we're actually going to do a hypothesis test, then we're going to do a confidence interval for it. So just kind of skip down here for a minute to the example. A researcher is studying the effect of allergy medication on the number of errors a participant makes in a sensory motor skills test. So we have the drug and the placebo groups. We have the means, we have the variances, and the sample sizes. And again, what are those means? 19 and 15 are what? What do they represent? Look at the thing. I kind of hammer this because people they get caught up in the numbers and they forget what it is they're measuring or what it is they're crunching. 19 and 15, yeah. Yeah, the number of errors. You're comparing the number of errors as a function of whether you took the medication or not. Okay, so let's do a hypothesis test for this and then a confidence interval. Our hypotheses are the same. And by the way, in the book, he might write the null hypothesis with the mu, and his subscript might be mu drug versus mu placebo. You could do it that way. You could do mu1 minus mu2, 1 and 2. I don't care. Either way is good. Yeah? Yeah? It's greater. It's more extreme. Right? That -7 is more extreme. You see? Right? Right. Well, think of it as more extreme is kind of more useful. Right, that's what we said. And again, that's because the probability of it happening is small. I'm just going to write these simple ones here instead of writing all of them. Okay. So which test are we going to do? Well, are both sample sizes large? No. Are the sample sizes equal? No. So then the question is checking for homogeneity of variance. For this example, do we have homogeneity of variance? Yeah, based on our rule, we have homogeneity of variance. Okay? Now, be very careful. You could be given an example that gives you the variances, but you could also, like the last example, be given given data that's the sum of squares. Don't just compare the sum of squares next to each other. Why? Because they get divided by degrees of freedom, and that can drastically change the numbers. So make sure you're comparing variances. Okay? So we have homogeneity of variance. So we're going to use the pooled variances test. So we'll use that version. How do I know if I have homogeneity of variance? You look at the variances. Where are my variances here? Where are the variances here? Yeah, S squared, 4 and 5. S squared is the sample variance. Okay. I'm going to write it up here, but it's going to be, there's going to be more to do with it. So let me just write it up here. You'll see what I mean. Okay? That's the t-test formula. But what do I have to calculate first? The pooled variance. Yeah? Okay. You have to calculate the pooled variance first, right? That's that S squared P. So let's do that. And again, just remember, this is a weighted average. And by the way, look what's in the denominator of the pooled variance. That's the total degrees of freedom for two groups, right? Okay, so that's just your pooled variance. Now you have to stick your pooled variance back into your T formula. Okay, question on where any of those numbers came from or anything? Okay. So now my T is going to be 19 minus 15. Those are my means. This is my pooled variance times 1 over n1 plus 1 over n2. Ugh, sorry, I did that wrong. You know what? I'm going to rewrite it. I hate not having eraser. Sorry. There you go. Okay. So then this is So that's my t. Now what? Now what do I do with it? Yeah, now I have to get a t critical value with how many degrees of freedom? Let's write them here. What are my degrees of freedom? You can do this math. I know it. What are the degrees of freedom? 32. Good. Okay. So we have to get the t critical value. So let's take a look at the t chart for a moment. Now the problem is, if you take a look at it, and you go down to, if you can see it, 32 degrees of freedom, you see it is not there. So what critical value are we going to take? 30, right? The next one lower, because we're conservative, at least in statistics. So we get a critical value of 2.042. Okay, so what do we do here? What is our interpretation? We reject the null, so therefore, what? Say it in words for this example. What's going on? Yeah. No, exactly the opposite. Because we rejected the null, right? The null is a statement of no difference, right? So, yeah, so there is, I say, but the way you worded it is great, right? There is a significant difference between people who took the drug and those who took the placebo in what? The number of errors they made. The number of errors they made. Okay? Questions on any of that null hypothesis testing? Because, sure, we rejected the null. There is a significant difference in the number of errors made as a function of whether they took the drug or the placebo. Okay? Yeah?
For the statement, the probability will be less than 0.05 detailed. Is the probability
No, no, no. The probability of getting a difference of 4 errors in this case, right? Assuming the null is true, right? If you assume the null is true, the probability of getting a difference of 4 errors is less than 0.05 two-tailed. It's rare. It's a rare occurrence. If the null is true, right? If the null, what?
So then you would use that statement.
Say, I would use what statement?
The probability is less than 0.05 detailed, or?
Is if you're rejecting.
Okay, yeah.
Right? If I'm rejecting the null hypothesis, right? If I'm rejecting the null hypothesis, what I'm saying is that this 4-point difference, if the null is true, this 4-point difference is so unlikely. How unlikely? Tiny, less than 0.05 two-tailed, that I say this must not be due to chance. It must be due to the drug in this case. Okay? All right. Now we're going to talk about how to create a confidence interval. Because again, a null hypothesis tells us significance or not, but a confidence interval will give me an actual estimate of the population difference, right, between those who take the drug and those who don't. Tells me how much error is associated with it, and can do a hypothesis test at the same time. So let's take a look at the equation for it. Like all confidence intervals, you start out with a point estimate, plus or minus a certain amount. How much is that certain amount? Like a standard error type thing times a critical value. That's what it is. So that's what we have here. The difference between the two means is my point estimate, plus or minus a t critical value times the standard error of the difference between the means. That's it. Now again, he writes it as mu1 minus mu2. I tend to do this. Confidence interval, and let's say it's a 95% confidence interval, 0.95. Okay? Either way you want to write it is fine with me. So let's create a confidence interval for these data. So we'll create a 95% confidence interval first. Is equal to, and by the way, he doesn't put it, you could actually put this in absolute value signs if you wanted to. Sometimes that's easier. Now, what's my T critical value going to be? What do I need to find it? To find my critical value here, what do I need? To find any critical value, what do you need? Degrees of freedom and an alpha level, right? So what's the alpha level going to be here? 0.05, 1 or 2-tailed? 2-tailed. Degrees of freedom are going to be what? 32. We're using the same critical value that we had before. The same critical value, so that's 2.042. What's my standard error? We did it. We did it. That's why I keep telling you the same thing. What is it? Look in your notes for that example. I kept stressing to you what it is. Where do I find the standard error? Yeah. Yeah, so what is it for this example? Yeah, exactly. Thank you. That was my standard error, right? That's what I calculated before. Okay. What does this mean? What does this confidence interval give me? How do I do the interpretation? Yeah.
95 certain that the
Interval.
yeah, but what falls into this?
No. How do we say it? That the interval contains, right?
That the interval contains
Yeah.
the
The difference. Okay. So let's make it specific for this example, right? I'm 95% confident that 2.52 to 5.48 contains the population mean difference in number of errors between the drug and the placebo group. Or between those who take a drug and those who would not be taking a drug, or those, who would take a placebo instead. Well, she asked for the whole thing, so I'll do the whole thing. I'm 95% confident that 2.52 to 5.48 contains the population mean difference in the number of errors between those who take the drug and those who take a placebo. Wait, hang on, everybody got it? Okay, yeah, go ahead.
That's how it should be written, even with the other confidence intervals, like in our SPSS assignments, we should say this interval contains.
Yeah, that's my preference.
Instead of our this value falls between.
Yeah, that's my preference. That's my preference. Yeah, you had a question? That's my standard error. Where's the standard error? It's the denominator of your t-test. That, like I said, do you remember I kept saying, this is the denominator of your t-test? Because you're going to just pluck it out and use it for a confidence interval. So again, so remember, right, in the confidence interval, what did I just do? I just gave you an estimate of the population difference in the number of errors between people who take the drug and people who would take a placebo. So we think it falls, right, between 2.52 to 5.48 errors. Okay? That also, hang on just a second, the width of that interval also gives me an estimate of how precise I think it is, how much error or uncertainty is involved in that estimate. Okay? Yeah? You wouldn't, okay? If you're doing a null hypothesis test, a t-test, with an alpha of 0.05, you should get the exact same results as a 95% confidence interval. The only reason that might be different is if one of them is using like 95 and the other is using 99 or 0.01 and 95 and something like that. It's the only reason. Okay? Now, so like I said, so there's three things we get from a confidence interval. We get the estimate, right? The estimate of the population parameter, in this case the difference. We get a measure of precision, how much error is associated with it. And we can also do a hypothesis test. So now, how do I do a hypothesis test with this confidence interval? Well, how did I do it with one group? How did I do a hypothesis test with one group in a confidence interval? What did I compare? What did I compare? When I wanted to find, right, I create a confidence interval and I said, yeah, I can do a hypothesis test with it. What did I compare? What did I compare to the interval? And you're all thinking, like, I'll know this for the exam. Right? I compared my hypothesized value. Right? Like if I hypothesized, I don't know, what was it? 3.5 days in the hospital. I compared that to my interval. And if it was in the interval, then I failed to reject. If it was outside the interval, I rejected, right? So what about here? What am I comparing to my interval? I'm comparing my hypothesized value. So what's my hypothesized value here? What's my null hypothesis value here? 0, right? 0 difference. That's why I wrote it the other way. Mu1 minus mu2 equals 0. I didn't write it this way for this example, but it's the same. If 0, so we could even draw this, yeah? This is 2.52 to 5.48 errors. Where's 0? Where does 0 fall? Yeah, like over here, yeah? So is 0 a likely value based on this data? No. So you'd reject the null hypothesis, right? If 0 falls outside of the interval, or again, whatever your hypothesized value is, if 0 falls outside the interval, we reject the null hypothesis. If it falls in the interval, then we fail to reject it. We have to keep it. Yeah? No, because there are times when you might hypothesize an actual difference. Remember I said, like if you're looking at men and women and you know that the difference is 30 pounds, so then you might have a null hypothesis of 30 pounds as your difference. No, because 30 pounds could still be directional. It depends. Like let's say I'm assuming there's a 30-pound difference between men and women, but I've come across a group of women that I think are particularly undernourished or anorexic or something like that. So then the hypothesized difference might not be 30 pounds. I mean, the null hypothesized difference might be 30 pounds, but these people, like this difference might actually be bigger. Now, if I was saying bigger, that would be directional. But if I'm just saying different, then I'm looking both ways. You know? So it's not the number that's making it directional or not. It's where you think your results are going to fall that will change that. I don't know is that helpful? Yeah? Okay. Other questions along that line? Okay. So now we know what to do with this confidence interval, right? We have it as a hypothesis test, and an estimate, and it's giving us precision. Okay? All right. Assumptions. You've seen these assumptions before. Now, the thing is here, independent random sampling. We've talked about independent random sampling. We've talked about how rare it is to get it. In this case, though, when you have two groups, you have an additional advantage. You may not have random sampling, but if your groups are not predetermined, you should have random assignment. That is, right, you put, some version of all the names in a hat and randomly pick them out for which group they belong to. Okay? So what's the problem? Let's say you've developed a new therapy for treating phobias, and you put out an ad that you're looking for 30 phobic people to take part in this study. And the first 15 people who show up, you put in the therapy treatment, and the other 15 people, the next 15 people, you put in the control. What's the problem with that? It's not random. What's the problem with it? Yeah, go ahead. The first 15 people might be more phobic. They're certainly more eager, right? They might be more willing to take part, So it's like a self-selecting group. So you have to have random assignments when you're talking about this stuff. Normal distributions we've talked about. Homogeneity of variance. That's our sort of new thing. We had talked about the variance or the standard deviation being the same before, but now it's a little fuller. You don't have to worry if both of your sample sizes are very large, right, 100 over each, or if your samples are the same size, okay? And if your sample variances are very similar, and that's our rule for very similar. So you don't have to worry in that case. All right, let's talk about the separate variances test for a minute. Homogeneity of variance, yeah. When the variances are? Yeah. Okay. Let's talk about testing for homogeneity of variance for a moment. I told you your rule is going to be if one is no more than twice as big as the other, right? But you're going to come across a couple of other things, other ways to test it. One of which is very easy, and you'll see it all the time because SPSS spits it out automatically. And the other, we'll talk about it when we get to chapter 12. Okay? Yeah, they just put it in this whole section. First of all, let's talk about what the null hypothesis is for homogeneity of variance. The null hypothesis is that the variances are equal. Population variances are equal. That's my null hypothesis. In essence, this is one of those weird times where you sort of don't want to reject the null, because it might make your life a little more complicated. Ideally in science, we don't want or not want a particular result, but we all get kind of tied to certain things. But so the one test, so the F-test, that's not the one that we're going to talk about a lot now. That's the one in chapter 12. But it's a very simple test, but it's not very reliable. The other test is something called Levene's test. Levene's test comes out automatically in SPSS. So it's useful. Now, in SPSS, how do we tell whether our results are significant or not? When we're doing it by hand, we're comparing observed values to critical values, right? But in SPSS, how do I know if something is significant or not? What do I look at? What do I look at in SPSS to determine if something is significant? Yeah. The p-value, what column is it called? It's not called p, it's called sig. Right? It gives you a value, like it gives you a t-value, and then it gives a sig column, and underneath it, it has 0.00 whatever. or a 0.75 or whatever it is, right? What do I compare that to? Alpha. Okay? Same thing here. So in Levene's test, you would get a value, and then you would get a sig result. If I got a sig, or a p-level, of that, would I reject or would I fail to reject the null? I'd reject, right? Because that's smaller than alpha. I want all of you to follow this, right? I'd reject. So therefore, do I have homogeneity variance or not? No. No. So in Levene's test, if you reject the null hypothesis, you do not have homogeneity of variance. In Levene's test, if you, yeah.
Oh, this, I'm not sure if it's connected, but on SPSS,
Yeah.
next to this on the column, it has confidence interval or something.
Yeah.
It's not the same as what our calculator would be. It's much less.
You know, it depends what it's doing. The confidence intervals, I can't remember. I know I think it's for one group it does something weird, or for two groups it does something weird. I don't remember. One of them it does something weird. Katie, do you remember? No, I know. That's why often, like, I won't ask you, or I'll ask you something from one and not from the other, because it does something different. I can't remember for the moment which it is. But yeah. You know, because it might be comparing it. Like I said, I can't remember which one it's doing it, but it picks a different number and it takes it around that.
I think I know what you mean. Yeah, we did that population mean.
No, in the confidence interval, I know that in one case, but I can't remember which one, that it creates an interval not based on what you think it's going to create it on.
Yeah, it was population.
But that might have been because you were hypothesizing. But that might have been if you were hypothesizing a value of 50. I'm talking about something else. But it could be that you are hypothesizing a value of 50. That happens. Okay? So anyway, so I want you to understand this. If you see this in Levene's test, and you see a sig value that's less than alpha, you do not have homogeneity of variance. You don't have it. And then you should read the T line that says for separate variances. That's when it becomes appropriate. You want the separate variances test then, not the pair, not the, I think in SPSS it says variance is assumed equal or not assumed equal. So then you'd have to take the one that says variance is not assumed equal. Okay, questions? Questions? No. Okay, yeah. No, you don't have the flow chart on your exam. You just write down those 3 questions and like which formula it is, you'll be fine. Okay? So if you don't have homogeneity of variance, then you do a separate variances test. And as I mentioned before, the problem with the separate variances test is finding the right critical value. In order to find the right critical value, we have to it's called the Behrens-Fisher problem. I don't care. You don't need to remember that. But it's finding the right degrees of freedom. For this class, and we'll do an example, not today, but next class. For this class, you're going to use the same degrees of freedom for a pooled variances test as for a sample variances test. It says it at the bottom of the flow chart. Okay? Normally, you'd have to find a different set of degrees of freedom for pooled and separate. For this class, you can use the same degrees of freedom, n1 plus n2 minus 2. Everybody got that? Same degrees of freedom. So I don't want you to get confused. Okay? So then I'm just going to comment on this, and then we'll do the other example on Wednesday. I mentioned that before. When to use a 2-sample test. We talked about it. The only difference is here, I just want to point out, a 2-sample t-test is appropriate only when your dependent variable is interval or ratio. Although I know lots of people that use it with ordinal data, so you need to know your discipline. And the other thing is that the independent variable is assumed to be categorical or nominal, right? 2 categories, boys, girls, yes, no, drug, placebo, right? Republicans, Democrats, whatever. Sometimes what people do is if they have a quantitative variable, they do what's called dichotomizing. So if I took you guys and I gave you an anxiety measure, and then I just said, okay, everybody above this score is a high anxiety and everybody below that score is low anxiety, that's called dichotomizing. You set them up into two categories, even though the original number was a quantitative thing. That's not the best thing to do for this. People do it, and so if you come across it, I just want you to know about it. Not the best way about doing this kind of research. Okay? And you would pick a different kind of analysis would be better. All right? Okay, we'll do the next example next week, next Wednesday.